Welcome to Chemistry 102. Notice there was a lot of handouts at the door. Don't worry, that's for about the first 2 weeks of class. There's obviously the homework like normal, and then there's two kind of extra sheets. The first one talks about line drawings, and that's what we're going to talk about today in class. That's what we're going to talk about and do in lab tomorrow. And so that's just a little extra sheet that kind of outlines and gives you something to read, since this isn't something that's in the book. And then the other kind of thicker one is called Reaction Guide, and that's actually for the first 6 chapters of reactions. So that contains every reaction that is going to be covered in class in the first 6 chapters in organic chemistry. And so if it's not in there, then we're not going to cover it and it's not going to show up on a test. And so that guide, to me, it's almost like a giant study guide. It's also kind of walks you through and gives you some additional reading on how to think about reactions, and it's something that's probably good and worth reviewing. Hello, Jasmine, who's late, her first day.
Sorry.
You guys all know Jasmine, right? Jasmine, you'll unfortunately get to know all these people. So pick up one of everything, except apparently we're short a D. Did someone find it yet? Oh, Jess stole it. So there should be one of everything there for you. Yes. So what we're going to be doing this semester is we're going to be starting with 6 chapters of organic chemistry. Then we have a chapter that's on stereochemistry, which is sort of halfway between organic chemistry and then the biochemistry. And then the last bunch of chapters for the second half of the semester is going to be all biochemistry. And so there's a pretty sharp transition between material covered in the first 6 chapters and the material covered at the last 6 or 10 chapters. And the key, though, is that all the material in the first 6 chapters we use in the following chapters. We just don't use it kind of as heavily, and we don't use it in exactly the same way. But it's important in this class that sort of that long-term functioning is in there, because when we start talking in chapter 26 about carbohydrates, we'll be making references back to all the things that we talk about in the first 6 chapters on organic chemistry. The other thing is that the first 6 chapters are kind of nice in that they're all very similar to each other, in that we simply cover 1 or 2 functional groups per chapter, and once you figure out the pattern, once you figure out sort of what do I need to do on each chapter to learn, then it's very easy to do well. So for instance, if you work really hard on test 1 and you master it, then exam 2 and exam 3 are really easy, because it's the same type of material presented in the exact same fashion, and so you should be well prepared to study for those. Now, if you struggle with chapter 1 or the first 2 chapters, 19 and 20, then what you're going to have to do is double down, because you're going to have to learn some of that stuff that you didn't learn in chapters 19 and 20 in order to go on and take exam 2 and exam 3. And so this class has a very sharp learning curve at the beginning of the semester, meaning it's the hardest the first couple of weeks as we're learning all this new stuff. Then it kind of gets a little easier once you've got the pattern for the organic chemistry classes. And then I would say the last bunch of chapters are kind of like this, meaning it's just, intermediate, how about? And so not too bad. So work hard the first first couple weeks here, and then, the next couple weeks kind of will be a little bit easier. And if you don't work hard the first couple weeks, you'll dig yourself such a big hole that it's almost impossible to recover. So this class is a little bit on the front-loaded side, which is okay. It's the second semester. You guys are used to working hard, and I know you guys are all capable of it. And so what we're going to do for this week is we'll start in and we'll review Lewis structures, and we'll talk about what I call line drawings. It's a way of drawing organic molecules that is much, much simpler, much, much quicker than drawing Lewis structures. And so it's what Jay does, because it's the easiest and the laziest method for doing it. Tomorrow in lab, you need to go and remember to buy the lab book from the bookstore. It should only be 4 or 5 bucks, and it should have all the labs that we're doing, in lieu of the $200 lab manual that you would normally buy. We'll be doing the very first lab in there. It's called Lab 19, Review of Lewis Structures. So if you remember Lewis structures from first semester, then you're golden. If you don't, then this is a good refresher to get us going and moving. And then, Wednesday and Friday will be normal lectures. Thursday, what we'll do is we'll have it be a safety quiz day. So there'll be a quiz on safety, somewhat similar to your original safety quiz, but different questions. And I think I might add a section of questions in there on general laboratory technique. And this is in lieu of giving an actual safety lecture, since all of you have had chemistry before. And Jasmine, I admit it's been a little while ago since you had chemistry, but all the safety stuff should be, easy to remember, or just go through that safety sheet and you should be okay. And then we'll consider the rest of that Thursday a work day, because we'll have a bunch of homeworks and worksheets, and I really want people to make sure they build that solid base and foundation. And then, Friday will be just a normal lecture too. Let's see. So what we're talking about is organic chemistry. And what we probably want to contrast it or compare it to a little bit is some of the chemistry we've done before. The first definitions of organic chemistry simply said that it was anything to do with living organisms. And so the idea was that at one point they thought that there was some vital force or something that made living organic molecules different than inorganic molecules. So that's sort of in contrast to what we consider inorganic chemistry, which was considered chemistry of minerals, rocks, and non-living material. Now, that whole idea that organic chemistry is anything to do with living organisms, or that the compounds in organic chemistry come from living organisms, has been since disproven. And it was disproven by simply finding a process, a chemical reaction that could be performed that produced a molecule that normal living organisms possess, but was instead made in a beaker. And so that's not the best definition for organic chemistry. Another definition of organic chemistry is that generally it is made up of molecules that contain carbon, hydrogen, oxygen, and nitrogen. And you know that those are the chemicals of life if you ever take a biology class. Now, we're going to throw in a little bit of sulfur, a little bit of phosphorus, a couple other elements here and there, but for the most part, that's 99% of the molecules that we're looking at are simply carbon, hydrogen, oxygen, and nitrogen. And so we'll spend most of our time focusing on that. What that means is that most of these compounds are molecular in nature. Now, what's the opposite of molecular? Ionic. So notice in first semester, we probably spent about 75% of our time on ionic compounds, and we didn't talk about molecular compounds too much until we got to chapter 11 and Lewis structures. So what's some of the differences between molecular and ionic compounds from first semester? Okay, which one is which? Yeah, metal, non-metal, and these are non-metals, non-metals. Does everyone remember the difference between metals and non-metals and what's in between them? The metalloids, right? And really what we're simply reiterating with that is that we're going to deal with stuff that are mostly carbon, hydrogen, oxygen, and nitrogen. What's another difference? Oops, yeah. Yeah, this was cations and anions. And then molecular compounds didn't form cations and anions. So this was because they sort of lost or gained electrons, right? What do we know about molecular compounds? We share electrons. And that's why we're eventually going to go and talk about Lewis structures, because that's how we show it. Yeah, in water, right? And does not How about another one? What do we know about sharing electrons versus ionic bonds as far as their strength? Yeah, these are strong bonds. These are weak bonds. And so since they're weak bonds, this generally means we have low melting points and boiling points compared to ionic compounds which have high melting points and boiling points. And then the last one we want to talk about is solubility. And we're going to spend a half a day probably talking about solubility at some point, reviewing chapter 14 on it. But molecular compounds, it really varies considerably whether they're soluble or not, whereas ionic compounds are generally soluble. Now we know that some ionic compounds certainly are not soluble, that they form precipitates and reactions, but these are again general rules. You can certainly find molecular compounds that have stronger bonds than ionic compounds, but as a general rule, most molecular compounds have bonds that are considerably weaker than the ionic compounds. Varies. So the solubility, oops, I should have put that down, varies. Meaning that some compounds are going to be highly soluble and some compounds are going to be highly insoluble. Okay, since we're talking about molecular compounds, for the most part, and we're going to want to draw their Lewis structures, we need to have a little bit of review about Lewis structures. So what's important in Lewis structures? Yeah, we have to have the octet rule. So we're always trying to have 8 electrons. And we know, of course, that that's except for hydrogen and helium, because there's always got to be an exception to the rule. And what that means is that limits the types of shapes that we can have in our Lewis structures. For example, if we look at carbon, how many valence electrons does carbon have? Yeah, it has 4. And so we draw it like this. And so what that means is that in general, carbon makes 4 bonds. But that those 4 bonds can be in a variety of different forms, right? For instance, we can have carbon that has 4 single bonds, or we can have a carbon that, say, has double bonds, like in carbon dioxide. We can even have a carbon that has a triple bond, like, say, in that molecule HCN. And so we can have single, double, and triple bonds, but notice that the bonds always add to 4, right? So anytime you draw a molecule, you have to draw your molecule, simply count to 4 and say, does carbon always have 4 bonds? If you draw a molecule where carbon doesn't have 4 bonds, it's wrong. And so if you can kind of remember some of those basic rules, you'll find drawing these Lewis structures and kind of reviewing them pretty easy. But part of the problem is going to be that when we start talking about line drawings, we're going to abstract some of this drawing and counting, in which case you have to be extra careful and always remember to go back and say, okay, even though we're not drawing all the bonds necessarily, I still have to remember to mentally kind of count them in my head. So what about oxygen? How many valence electrons does that have? 6. For Hayton morning, Jess is doing pretty good here. She's kind of rocking it up on all the rest of you. So if it's got 6 valence electrons, how many bonds does oxygen want to make? Yeah, it generally wants to make 2 bonds. And so remember, we generally saw oxygen like this, where it's got 2 lone pairs and 2 bonds, or we saw oxygen in a compound, for instance, that had a double bond, like in CO2. Now, we have to be careful. Occasionally, if we form ions, we can break some of those rules in which we might have an oxygen that looks like that, in which case it has a -1 charge on it. So it only has one bond, but notice it has an extra set of lone pairs on it, right? So remember, when we have ions, when we have extra electrons, or in the case of cations, if we're missing some electrons, we can sometimes break that octet rule. Or not really, I shouldn't say we're breaking the octet rule, we're still following the octet rule, we're just breaking that general rule of only making 2 bonds. Okay, what about nitrogen? How many valence electrons? 5. And so how many bonds does nitrogen generally want to make? Yeah. It will make 3 bonds because it will want to share or gain control of 3 electrons. And so that means that we can have sort of nitrogen like this. Or we can have a nitrogen with, say, a double bond to something, and then another set of electrons. Or we can have nitrogen with a triple bond to something, and then it has a lone pair of electrons on it. Notice that nitrogen pretty much always has that lone pair of electrons. And then, of course, we can form ions, in which case we can have something like this type of molecule, where nitrogen actually has 4 bonds. And does anyone recognize this? And then it has a little +1 charge associated with it, whereas that had a -1 charge. I mean, normally we wrote ammonia as NH4+, right? That's our only cation. And so what we'll find is when we get to nitrogen, probably, especially in the normal chapters, 99% of the time nitrogen will form 3 bonds and just follow the rules. But occasionally we can have nitrogen form ions, in which case it will have 1 extra bond. What's the last element that we need to talk about? Yeah, hydrogen's pretty easy. It's got 1 electron. It doesn't obey the octet rule because it doesn't have p orbitals, remember, and so it only forms 1 bond. And so when you see hydrogen, you should see it look like that, where it's attached to, a carbon or something. Okay, so that's some basics on Lewis structures. Hopefully that's all review. Hopefully that's all something you kind of remember from first semester, or in Jasmine's case, all the way from last year, a long time ago, where, we're going to have a lab on it. You'll build the models. You'll get lots of practice. Because one of the things that we're going to be doing constantly is drawing molecules. And the reason that we need to kind of know our Lewis structures is that we do need to keep track of where the electrons are, and we are going to keep track of what's bonded to what. And so if in the back of our mind we're always doing little double checks and mentally counting to 4 every time we draw a carbon, mentally counting to 2 every time we draw an oxygen, and mentally counting to 3 when we draw a nitrogen and a hydrogen 1, if we can count to 4, gosh, we got a lot of the math done in this class. That is one of the advantages, or some people consider it an advantage second semester, some people consider it a disadvantage in that there's a lot less math this semester. If you can count to 4, you're doing pretty damn good in class. And everyone's got 4 fingers, right? Got no gimps in here that are missing a few, anything like that? Haven't roped anything off yet, Jess? Not yet. Okay, so we're going to talk about sort of 4 different ways to draw molecules, or to represent molecules. And each method sort of has its advantages, and each method sort of has its disadvantages. And which one we use in any given situation sort of depends on what we want to focus on. We'll probably find that 99 times out of 100 by the end of the semester, we're drawing stuff using line drawings, which is what's going to be new. So we can have what are called molecular formulas, in which we simply list the atoms and numbers. And so that's kind of like in first semester we would have simply written CH4. Meaning it tells me I've got a molecule with 1 carbon, and it tells me I've got 4 hydrogens. We can have structural formulas, in which case what we generally do is we draw the Lewis structure. And so for a simple molecule like this, we just draw the Lewis structure like this. Now, I should also point out that we're going to draw a bunch of examples under each of these columns, so leave plenty of space in your notebook. There's going to be a total of 4 columns, obviously, right? Or, you can organize the information kind of however you want, I guess. We have what's called condensed. And this is sort of halfway between a Lewis structure and a molecular formula, in that we simply list the atoms, but we kind of tell which order things are connected in. Now, I have to be honest, for the simplest example here, it's exactly the same as the molecular formula. So it's not a good example of it. We'll do more complicated examples next and show you what we mean. And then, of course, the last one is line models. And I'm going to go and give some details of this on a separate page, since we want to do this. Line models are a really shorthand way to draw organic structures that contain lots and lots of carbon atoms. And so what we say is that any vertex is a carbon atom, and we tend to leave off all hydrogen atoms. And so we don't bother drawing the hydrogens because it's a lot of work. And then we just represent other atoms as normal. And what that really means is that, for instance, if I take a look at CH4, that's simply a dot. We don't draw 4 hydrogens on it. That dot simply represents that carbon atom. Does that kind of make sense? And the reason we want to switch to thinking about things in terms of line models is mostly because we're going to be drawing lots and lots of molecules. We're going to be drawing very large molecules. They might have 8 or 9 or 10 carbon atoms in them. And drawing all the hydrogen atoms on them are tough. For instance, if I take a look at just a Lewis structure that looks like this. 1, 2, 3, 4, 5, 6, 7. And then I have to go and I have to draw all these stupid hydrogens on it. Holy cow. I'll spend more of my time writing C and H on a piece of paper than anything. And you guys will be sick of writing C's and H's. And so instead what we say is that instead of having something that has 1, 2, 3, 4, 5, 6, 7 carbons like that, we'll simply draw a zigzag line with 1, 2, 3, 4, 5, 6, 7. That is the same thing. And notice I leave all the hydrogens off, so it's pretty, it's a lot less work. Notice it's a lot cleaner than my Lewis structure. I mean, I have to admit, it's not like I tried to draw my Lewis structure really nicely, but I also didn't try to draw it messily. That's kind of how I would just normally draw it. Some of the bonds are a little longer, some are a little less, and it's just a lot simpler to draw a nice little line structure like that than to draw a molecular formula or a Lewis structure that has all those carbons. And if you look at it, it contains all the information. It tells me that, for instance, the first two carbons are bonded together. That's what the line represents. And it doesn't, of course, tell me some of the information. It doesn't put the hydrogens in there, right? But how many bonds does carbon have to have? 4. So like this carbon at the end, how many hydrogens does it have to have? If it's got a bond here, then we should have to draw like 3 hydrogens if we wanted to, right? And if I pick a carbon in the middle, how many carbons does this bond here have? How many bonds does that carbon have already? 2, 1 to either side. And so, I would normally have to think about the fact that, remember, there's 2 hydrogens there. And so the bad thing about line drawings, at least in the beginning, is if we forget that all those hydrogens are really there. And what we generally do when we draw a line drawing is if there's a hydrogen that takes place in a reaction, we draw it on there to help us out and to help us think about it. And then, after a while, you can stop drawing them on there if you want. But always remember that there's, those hydrogens floating around. So like I said, for the simple example here, the line model is simply a dot. You really can't draw it very easily. Now, if we make the next compound in that series, C2H6, that's its molecular formula, simply 2 carbons and 6 hydrogens. And then if you thought about it and said, how am I going to draw that Lewis structure, you'd realize that the only possible Lewis structure is to have the carbons bonded to each other by a single bond, and then have each carbon have 3 hydrogens attached to it. That satisfies everyone's octet rule, and everyone's pretty happy with that. And then the way we represent these condensed structures is it's kind of halfway between the molecular structure and halfway between the structural one, in that we'll simply say I've got a CH3 group and a CH3 group. So what we're really saying is that this first carbon here has 3 hydrogens attached to it, so that's CH3. And then by putting another carbon here, we're automatically saying that those 2 carbons are bonded to each other, because we know carbon has to have 4 bonds. And then, of course, we have 3 more hydrogens on the second one, so we just write CH3 again. Now, I have to be honest. To me, the condensed structures are the trickiest, because they sort of make the most assumptions. They don't necessarily straightforward tell you what's bonded to what, and there's a lot of variety in the way that people sometimes represent these molecules. And so that's probably the hardest one. It's actually the one we use the least in class, but that if you're reading a book and it's in line, they use the most because it fits on one line of a textbook, as opposed to a structure which has to be a separate picture or a figure. So they sometimes use those condensed structures quite a bit. And so we have to know how to interpret them. And then for a line model, it simply is a line, and each end is considered a carbon atom. So what do you think the next one we should look at is? What would be a next good example? How about C3H8? In which case, for the Lewis structure, we realize that it's a bunch of the same thing that we've had, and that the carbons have to be bonded together, and that we have to have hydrogens to kind of fill out all the octets. And sometimes we'll refer to that long carbon chain as a carbon backbone, because what we're going to find is that the core of any organic molecule is simply a long string of carbon atoms that are bonded together. And if I want to do the condensed model, all I do is I break it apart and I say, well, I've got a CH3 group here. What have I got here? CH2, and here I've got a CH3. And for a line model, it's just an upside down V. And I got to be honest, it doesn't matter which direction you draw it. I tend to always go up and then down, but there's no reason that says you can't go down or up. Or quite honestly, if you want to draw it like this, you can. You know, anything that has kind of 3 vertices really is an example of that molecule. Okay, so what's next? Yeah, C4H10. And I got to be honest, I'm going to be getting a little lazy here. This might be the last time I bother drawing a Lewis structure. So we're going to have an entire lab kind of drawing Lewis structures, but mostly it's because I want you to start getting practice on, counting up the number of atoms and bonds, get used to those shapes. And then I have to admit, we just start using line drawings almost exclusively by chapter 20. And then if I looked at the condensed structure, what would it look like? And I've got 2 of them, right? And a CH3. Now, that's the easiest way to do it. Occasionally, you'll see it drawn like this. So does that make sense? That if I've got 2 CH2s smushed in the middle of that molecule, I could just write CH22? Okay, so one of the things that's also tough about condensed structures is we start to throw in little shortcuts like that. Meaning, if you just write CH3, CH2, CH2, CH3, that's pretty easy. If you start throwing in too many parentheses and things like that, it gets a little harder. What you guys will want to do at some point is practice going back and forth between those. And you also want to practice, and this is what the first homework is, going back and forth between those two models. And so for here, it's just 4 carbon atoms stuck together in the shape like that. Now, can you draw it like this if you want? Sure. Or can you draw it, you know, with the going down and then up? Sure. There's all sorts of ways you can draw it. You'll notice that I tend to draw them all the same way, mostly out of habit. But certainly you can draw it many, many different ways and have it be correct. Okay, so if I do C5H12, I'm going to skip the Lewis structure because I'm a lazy bum. Here, the part that would change is instead of a 2, I have 3 CH2 groups in there, right? And then here I just have 5 lines stuck together. So, have you noticed a pattern in these formulas here? So notice mathematically the pattern is, whatever number that is, then the hydrogens are 2n plus 2, right? So if I've got 5 carbons, I have to have 10, 11, 12 hydrogens to complete everyone's octets. And those are called sometimes homologous series. And really what it does is it says that for any set of compounds that we have, we can always come up with a general or generic formula like that that describes them. And so sometimes you might see that written down and it simply says hydrocarbons with the following formula all do this or something like that. And so just realize that that's a cheap way of saying anything that's just got carbon-carbon single bonds in it like that. Okay, let's mix it up a little. Let's take a look at a Lewis structure that looks like this. So here's C5H12, and so one Lewis structure, actually let's just do the next one up. We'll be less lazy. C6H14. We can of course have all the carbons in a nice row, and maybe Jay's laziness will extend to simply not drawing all the stinking hydrogens on there because he's tired of it. And that of course, you know, looks like CH3, CH2, 4, CH3, and it's just 6 in a row. 1, 2, 3, 4, 5, 6. But there's additional Lewis structures that we can draw for this molecule. And so there's additional correct Lewis structures and molecules. And we're going to call these, let's see, sometimes they're called constitutional or structural isomers. Now we're going to go into a little bit more detail later on, but I want you to just kind of have this in the back of your mind. It basically means it has the same formula, but a different structure. And we'll find that this idea of isomers, things that have similar formulas but different structures, is a reoccurring theme. So in this chapter, we'll talk about constitutional or structural isomers. When we get to chapter 20, we'll talk about what are called cis and trans isomers. And then we have an entire chapter, chapter 27, on what are called stereoisomers. And so this is one of those things where it starts off nice and easy, and it's going to get a little bit more complicated as we go forward. And what it simply means is that that Lewis structure doesn't have to be exactly that way. What if, you know, I just stuck one of the carbons off of another one? In which case, you know, I've got 3 hydrogens here. Now I've only got 1 on that carbon. This one's got 3. This has got 2. This has got 2. This has got 3. So that when we come and write that condensed structure, it's going to be a little different. I'm going to pause here because I want everyone to draw that out so that they have it. And I want you to kind of pay attention because this next part is a little tricky because there's more than one correct answer. And so here's one set of things, and we'll do the other. Jasmine, when's your basketball practices? Sometime between 2 and 6. Wonderful. Jess, when's rodeo practices for you? Do you even start for a while?
We don't start for a while, but 3:36. But when we do start, we'll be traveling to rifle. The first part of it, practice in the indoor. The arena won't be ready yet.
So yeah, it'll be late days for you. Oh well. I'll have to go with you sometime just so I can ride a horse. It's been a while. I sold mine. You guys remember that, right? I'm kind of sad.
The issue about it too, we usually puts the practices the night before workouts. Then we get back at 1 in the morning and he expects us to be up at 5 in the morning to go to workouts.
Yes. So, notice that if I'm trying to draw this, write this structure as condensed, I've got this first CH3 group, and then notice I've got a CH group, right? And attached to that CH group, I have one CH3, so I can put that in parentheses. And if I want, I can either write it like this, CH2, CH2, CH3, or this would also be an acceptable structure. I've got that CH group, I've got a CH3 stuck to it, I've got a CH2, and I've got, notice, 2 of those, so I could do that. I could even get really tricky and say, well, this CH group actually has 2 CH3 groups on it. So I could do something even trickier like this and say there's 2 of these groups. There's a CH group, a couple CH2 groups, and a CH3 group. So there's many correct answers for something like that. And then for line drawings, the way we do that is I've got 5 carbons that are in a row, and then I've got 1 carbon that's stuck someplace pointing up like that on the second carbon. Ugh. Or, you know, an equally correct structure would be to show it pointing down. And although generally I draw the first one up and then the second one down, I don't know why. Like I said, I just get into habits after a while. So there's a lot of different ways to do this. And in fact, we could come up with some other structures for this too, right? What if instead of having 5 carbons in a row, I only had 4 carbons in a row, and then I stuck a carbon up here and say a carbon down there? So I would have something like CH3, I'd have 3 of them, a carbon, a CH2, and a CH3. So notice that here's my 3 CH3 groups. Here's my lone carbon with no hydrogens on it, a CH2 and a CH3. And then for a line drawing, it's just 4 carbons, and then 1 carbon has 2 additional ones off it. What I want you to think about is I want you to be proficient with those condensed structures, but realize that for the most part, we're really going to be using line drawings for everything. Because I got to be honest, we are lazy. And notice that, heck, you know, here I haven't even put the hydrogens on, and, you know, it just takes too much work. I'm lazy. Okay, let's look at some other things. This is a little bit in advance in that some of these molecules we're going to start to look at are in chapter 20, so we're not going to be using them for a while, but I want to kind of draw them in there just so that we can do it. Taylor, I can go back. Remember, it's all on. Okay, what if I have a formula like C2H6? Well, I'm sorry, C2H4. Well, this is stuff that we're going to see in chapter 20, meaning chapter 20 is about compounds that have carbon-carbon double bonds and triple bonds. We're going to learn how to draw them in chapter 19. So that's why I just kind of put that chapter 20 there. Meaning it's something that we're going to do again, but I want you to at least kind of think about it. So if I draw the Lewis structure, the only correct Lewis structure we realize is to draw something with a double bond. And the way we draw that for a condensed structure is we simply say CH2 double bond CH2. Or, I got to be honest, sometimes they'll be tricky and we'll just write CH2 CH2, and you have to be smart enough to realize that since carbon has to have 4 bonds, that there has to be a double bond somewhere in that molecule. So like I said, always keep in the back of your mind 4, 3, 2, some numbers like that. And then for a line drawing, we just draw a double bond like that, and the idea is that at this end is a carbon and that end is a carbon. Or if I have something like, say, C3H6, let's see if I got that right. I want to have 1 carbon-carbon double bond in there, so how many hydrogens do I need? 1, 2, 3, and then this guy must need a hydrogen, so 1, 2, 3, 4, 5, 6. And so here we could label this as CH3, CH, double bond, CH2 is probably the easiest way to do it. But again, you know, sometimes they're bastards and they don't make that double bond explicit. I like to put it in there. I consider it not that much extra effort, and most computers have an equal sign on them, which is all a double bond really is. And then if I were to draw that in a Lewis structure, I just would draw, you know, here's my 3 carbons, or not a Lewis structure, a line drawing, 1, 2, 3. So we just draw a double bond by drawing 2 lines on it. And then if we have something with, say, a triple bond in it, so we'll draw that last one with a triple bond. You know, it looks something like this. Let's see, that would be C4H, 1, 2, 3, 4, 5, 6. And so notice that that C2H4, C3H6, C4H6 doesn't really give you an idea of what the structure is. That Lewis structure tells me automatically that I've got a triple bond in it very easily. It's very obvious. The condensed structure, if it's drawn decently, like this, tells me automatically that I have a triple bond in it. But if people don't explicitly show that, then it's not so obvious that there's a triple bond there. But if I draw the line drawing, it's pretty obvious that if I draw it like that, that there's a triple bond there. So to me, Lewis structures contain the most amount of information. They tell you the exact structure for it. The molecular formula, that C2H whatever or C4H6, tells me almost nothing about the molecule without at least thinking hard about it and drawing a Lewis structure. The condensed structure is kind of halvesies. It tells me a little bit about the Lewis structure, but it leaves a lot to the imagination, right? And then line drawings, to me, are the best. They give me all the same information a Lewis structure does, and they're faster to draw. Now, admittedly, we're not drawing the hydrogens, right? But remember, you guys can all count to how much? 4. So, you know, if you had to draw the hydrogens in this molecule, you'd say, oh, there's 3 hydrogens on this one. This one needs 2 more. This one's happy because it's got 1, 2, 3, 4 bonds. And this one at the end, you know, has to have a hydrogen on it because of that. So line structures aren't perfect. They're not the end-all and be-all of drawing. In the best of all worlds, we'd always draw the full Lewis structure. But we'd also find that pretty quickly it's pretty tedious and hard and a pain in the butt. And so we'll always, or at least I always, default to line drawings. That being said, when you have a test question that simply says draw this molecule, you're allowed to either choose Lewis structures or line drawings. It's up to you, whatever you feel most comfortable with. The only caveat I'm going to say is that when I draw stuff on the board, I do draw line drawings 90% of the time. And so sooner or later, you kind of got to get comfortable with it. But I usually will always include one example using a Lewis structure because it shows more information and details. So let's see. Some other types of things that we can draw. What if I want to, say, throw a chlorine on there? So say I've got C2H5Cl. So if I draw the Lewis structure, you know, we can figure out that one of those carbons has to have a chlorine on it. And if I draw the condensed structure, we just draw a chlorine just like a chlorine, so Cl. And if I draw a line drawing, all I do is I draw, you know, the two carbons, and then I usually will either draw a short dash to like a chlorine like that. Or I got to be honest, sometimes I'm lazy and I usually draw the short dash at least, just so that it's obvious that that's a carbon and that's a carbon. Now notice that I've been drawing dots where the carbons are to get us started. It's a good habit if you guys are drawing molecules to draw the dots sometimes, because it really helps you to remember where the carbons are and count them pretty easily. A lot of times I'll draw the dots on there, but a lot of times if we're just trying to do something quick, I won't bother drawing the dots on there. But if you're not certain whether a line is representing a carbon atom or if it's just like going to that chlorine, you know, if I drew something like this, the question is this is a carbon, but did I really mean to have a carbon there? Well, the bond's shorter, so we should say no, right? But, you know, at some point, if you're not careful, that becomes almost the same length, and so it's a question of, is that supposed to be a carbon there or not? And so in a picture, if I draw it especially, I'll always draw little dots on the carbons for you if it's unclear. But I try to be pretty good and neat, and you know, most of the time I manage to do it, but sometimes I have to admit I fail. Last thing we should maybe look at is how we draw oxygens in there. Like say for instance, if I've got C2H6O, there's a couple different ways that I can draw that molecule. I can actually draw it like this. Oops, wait. Yeah. Right? Or technically, I can also draw it like this. And so, again, just the formula that lists the carbons and the hydrogens, that C2H6O, doesn't tell me which of those two molecules is intended. And so it's not the best way to represent a molecule. We'd be much better off, you know, writing it a different way. Now, sometimes you'll see this written as CH3CH2OH. That tells you which of the two you're looking at, right? Because it tells you that, you know, the two carbons are bonded together and there's an OH group. Whereas down here, you'd have to write CH3OCH3. And so the condensed formula contains a little bit more information. It allows us to tell the difference between those two molecules. And then if I'm drawing a line drawing, you know, it's pretty easy to see the difference between those. Now, here's where line drawings get a little silly. When there's only like one carbon on each side, it's a little tough. But generally what we do is we just draw the oxygen as a vertex on it. So if you're really being lazy, you can do it like this. But I usually like to at least draw it separately so it's obvious what's there. So we won't try to draw it like that. So this is ambiguous, meaning there's more than one molecule that has two carbons, 6 hydrogens, and an oxygen. But you know, if I draw the condensed structures, that helps me to differentiate between the two. Certainly the Lewis structure differentiates between the two, and that those line drawings would allow us to differentiate between the two. And we're going to learn later on, I think this is like chapter 22 or 21, someplace way up there, but that's an alcohol, and this is what we're going to call an ether. Let's see, there's so many different orders the way I do some of these topics that I want to just see. Let's see. We have to move on to naming. Now I'm only going to give you the rudimentary part of it just because I want you to focus on the line drawings first, and then we'll pick up naming. And we're going to try to take this kind of slow to start with. So, and this is a lot of information to begin with. But if you're kind of thinking ahead and planning ahead, the next thing you want to do is memorize the name for carbon chains. And so the idea is that if I say meth, that means 1 carbon. And if I say eth, that's 2 carbons. And what's going to change is we're going to stick things on the other part of it. So for instance, if I say methane, A-N-E, right? That means that I simply have a carbon with 4 single bonds on it. Does that make sense? And so what we really are learning is we're going to learn 10 new words. Some of them are going to sound familiar. Some of them are just like random. And they're going to be the base for how we count carbons in organic chemistry. And so instead of calling something like methane, instead of calling it 1-ane and 2-ane and 3-ane, we've got words like meth and eth. So for instance, ethane, meaning eth means 2, and the A-N-E part means that there's only carbon-carbon single bonds, means that I have to draw this structure. But for instance, if I say ethene, E-N-E, that means that I've got a carbon-carbon double bond in the molecule. And so I draw this Lewis structure. Or for instance, if I say ethine, Y-N-E, that means that I've got a carbon-carbon triple bond in my structure. So the idea is that we're going to have numbers to count from 1 to 10, so meth, eth, and we'll cover the rest in a second. And then we're going to have different suffixes that we stick on the end of those molecules. And that tells us what type of what we call a functional group is in those molecules. So all organic molecules have that carbon-carbon chain as its basis. And then what differentiates them is whether I've, say, got a single bond, a double bond, a triple bond, an OH group, an oxygen stuck in the middle of the molecule, a nitrogen someplace on the molecule. That's what changes sort of the chemical properties and physical properties of those molecules. So we want to count from 1 to 10. And so that's going to be meth. I go back. And then I think we call it quits, because really we started at 7:45, right? And so we should go to about 8:45-ish. And I got to remember our new timings. Otherwise, I'd keep lecturing and forget. Okay, so meth, eth, prop, meth, eth, prop, bute, pent, 10. We're counting to 10 only. So this is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Hex is 6. Hept is 7. Oct is 8. Known is 9. And dec is 10. And so if I wanted to write, for instance, decane, decane, that A&E simply says there's 10 carbons in a row, so I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so, if we kind of draw the most simplest molecule for each one, the A&E ending, that's 1 carbon, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. And as a total aside, just to finish class up, how many people have heard about the chemical spill in Virginia? No one listens to the news? Apparently one of the coal processing plants there decided to spill, and last I heard it was someplace between 2,000 and 5,000 gallons of one of the chemicals they use to help purify the coal or do something with it. I didn't read too much about it because it was over break. But essentially the molecule that they're talking about, actually it looks like this, I think. Looks like that molecule. And I can't remember if it has a benzene ring on it or not, but it's an organic compound, and it turns out that this compound leaves a smell of licorice, is kind of its most notable thing. It's certainly not good for you. They say it'll stain clothes. You know, it's got all sorts of chemical properties, but you know, that's the chemical that spilled. And what I found funny is when I first read the news stories, one of the problems with organic chemistry, and maybe I'll just remember to print this out tomorrow, is that as far as I could tell from the news articles, they weren't sure which of the 3 chemicals it was, because they drew a draw. Some of the articles had that. Some of the articles had just an OH group there and not that extra carbon. And I can't remember, but you know, I can't remember if there was one that had it like this. And so they're talking about 3 different chemicals, and I have to admit all those look alike at first glance, but they have different physical and chemical properties, and you know, they're probably all toxic just because, but we'll learn that those 6-membered rings are not exactly happy friendly to the body. But we'll talk about that more when we talk about, oh gosh, I don't remember what number it is, like chapter 29 or 30 when we're talking about proteins and DNA. You may notice that that kind of looks like part of the DNA bases, and that's why it's not very good for the human body usually. There's other reasons too, potentially, but that's one of them. So anyway, let's end up right there. So tomorrow class starts at what time? 12:45. It doesn't follow the normal schedule because, you know, normally classes in the afternoon should start at 1 o'clock. It doesn't follow the normal schedule because we're a lab, and so we have to meet for extra time. So that means on Tuesdays and Thursdays you get a little bit less of a break than normal. And what we may do is, if people want, we might decide